In this video, we're going to take a look at how we can add diffuse shading to our Raymarched sphere. Once this is done, the object really starts to feel more 3D as we can rotate around it and see light and shadow on it as well. So this is going to be something very important to get our materials that are faking 3D shapes or objects to be drawn much more realistically. It was great that we're able to draw a sphere that's just the color red, but now we're actually going to be adding shading and calculating lighting on it. So let's take a look at how we can do that. So this is kind of what we had in our previous lesson or video where we have our red ball that's Raymarched in 3D space. What we're going to do is open up that material, same thing that we had from the last video, and we're going to add a new input here. So I added a new input, so we'll just click on the plus, add an element, and we're going to call it light POS for light position. And we're going to define a light position. So I'm going to create a constant 3 vector because it's going to be a position in XYZ in 3D space. And I'll just set the light position to like 1, 1, and 1. And that would pretty much mean that our light, if we look at this little axis here, our light would be 1 up in Z, 1 over in X, and 1 this way in Y. So our light position should be like here, casting down on the object. So that's essentially what I'm defining here. 1, 1, and 1, 1 in each axis, meaning that point right there. So that's kind of what we should end up with. So that's going to be the light direction. Now we have to use that light direction within our code. So I'm going to jump into Visual Studio Code so we can see that code a bit easier. And we're going to have to do something or utilize this light position that we're now defining. So in our code, we're going to make a bit of a adjustment. We're going to go up here. We're going to define a new float 3 called light direction. It's going to equal the normalized light position. So we turn it into just a normalized vector. And what we're going to end up doing now is when we detect that we're within the position of this object, or when we're intersecting with the surface, we're going to define the normals of that surface. So the normals will equal normalized ray origin minus the sphere center. And that's going to calculate our surface normals. And then we're going to use those normals to shade the object with lighting by doing a float, which will be our diffuse value. So diffuse is going to be the strength of the light on that surface. If the diffuse is 0, it's going to multiply that red color by 0 and just end up being in shadow. It'll be dark. If the diffuse power is like 1 because it's facing the light direction, then that part of the sphere will be red times 1. It'll be fully red. So that's essentially what this variable is going to do. So it's going to be the max of the dot product of the normal and our light direction. And then it has this max function here where it maxes out at 0. So like if we end up with a value that's negative, is this going to pretty much clamp it? So we can't end up with like negative values or any problems like that. So that's essentially what we're going to do. So that's going to be our diffuse function, or our way of calculating diffuse lighting. And now what we're going to do, make sure I have all our open and close brackets. Good. We have all that working. What we're going to do is multiply this diffuse value by our surface color. So right now we're returning red wherever those pixels are that make up that sphere. We're going to multiply this by our diffuse. So diffuse multiplied by red. So this essentially is our surface color. This is the strength of the light on that surface based on the light position. And we're going to multiply those two together, so it will darken the red if it's in the shadow area. It will brighten the red if it's closer to the light position. And that's really it. That's all we need to do. So if we take all this code now and pop that back into Unreal, update our Raymarched code with those new adjustments, what do we get? We get some error. I probably mistyped something. Let's see. So it says normalized we can't do, And that is my fault, because if I look at it here, normalized, did you mean normalize? That is what I meant, normalize. So I just added a D by accident. There we go. Normalized should be the code. Let me go update that just in case. So it shouldn't be normalized, it's normalize. Just a bad typo there. And now that we have that, look what we got. We got lighting on our sphere. Now you're going to notice something, and you may have noticed this before, but I wanted to wait for now to kind of really approach one of the problems that we have that you probably might have noticed. And that is, if we change our sphere center to maybe 50 on Z, Z is the up and down axis, as we can see here. And if we go 50 on Z, it should move the sphere up. But if I type 50 for the sphere center, it actually goes down. If I type 100, it goes down even further. That's wrong. That's flipped right now. And same thing for our light. Our light position should be 1Z, 1X, 1Y, but it's showing it in the opposite direction and downwards. So that's flipped as well. So our light position here and our sphere center here, it's kind of all thrown off. It's inverted. How do we fix that? There's a lot of things you could do. You could start inverting our light direction here, making it negative light direction, and that'll flip it and seem to work correctly. But let's fix this in a better way that solves it overall, because we'll run into these issues. So I'm just going to go back to the code, and to fix these flipped positions, what we're going to do is for our ray origin, we're going to make an adjustment where we're going to invert it. So we're going to do 1 minus, and then we're going to put that view direction minus world position in brackets. And that will flip our ray origin. And then our ray step, we're going to make an adjustment where it's not times 1, we're going to times it by -1. And after doing that, those two quick changes, timesing this by -1 and doing an invert on our ray origin, we'll copy all this code, throw it back into Unreal. It's going to solve all our issues. So now the light direction is specified correctly. If we want to move the sphere up or down, it's going to move correctly. Positive Z moves it up, negative Z will move it down. So that's all corrected now. All of our axes will work correctly when we're referring to them in our nodes here. So now if we save this, we pretty much have our Raymarched sphere that can be drawn in 3D space with some diffuse lighting. And we have the ability to move that light around. So I can make this a -1, flips the light to the other side, or 1, or maybe 0.2, 0.2, 0.2, place it at a different position. So we can flop all these lightings around, maybe -0.5, and then it puts it below. So now we're able to define a light position and have that shade our Raymarched SDF, or sign distance field or function of a sphere. And next, we're going to start taking a look at how we can add specular lighting to this. So not only diffuse lighting, specular lighting, which will give us a little bit of a highlight or a reflection of the light source, a faked reflection of the light source that we're defining. So that'll be the next step that we'll take a look at. So try this out, get it into your scene, and now we have our Raymarched sphere with lighting on it as well, and we can rotate around it, and it's starting really to feel like a proper 3D object. But again, it's really just all a material trick done with Raymarching and signed distance fields. So if you found this useful, if you're enjoying this, make sure you like, subscribe, comment below if you want to see specifically more videos on this topic. And if you're part of the Patreon, down in the description below, you'll also find the link to the Patreon. And for those Patreon users, again, you will get access to the PDF for this lesson, going over all the steps that we did in this video.